Welcome back and happy Thursday. Today we will finish up our module on virtual memory. But before we begin, a few administrative bits. Including today, there are 4 class meetings left. The home stretch is in view. Make sure you're keeping up with the reading, sections 10.1 through 10.6.4, pages 389 to 425. Some key dates: the residence halls close Wednesday, the 25th of November at 5 p.m. Make sure if you're on campus physically that you are on that deadline. The day thereafter, Thursday the 26th, is Thanksgiving holiday, so we will not have class on 26th. The last day of classes will be the 3rd of December. The day following that will be reading day, the 4th of December. Please watch out for Dr. Rasami's announcements for Division Day, when all the presentations and projects are given. The final exam period is scheduled for Thursday, the 10th of December, from 10:30 to 12:30 p.m., during which, for this class, we'll be doing project presentations for the final project. And then the last day of finals is the 11th of December, and at 8 p.m. on that date will be the deadline for submission via Blackboard of the final project. Okay. So when we last left off, we talked about applications and page replacement. And we said one approach is to keep a buffer of pages available in memory so that when an application refers to a page, or rather a bunch of frames in memory, so that when an application refers to a page, there are an available pool of frames that can be allocated. And we also mentioned certain special applications are given or allowed direct access to the disk, such as databases, because they know best how they're going to be using memory and therefore their pages. So let's take a look how frames might be allocated. And so every process needs a minimum number of frames, and some architectures use at 6 pages potentially per instruction. And these particular instructions can straddle more than one word. So the first word in the instruction or part of the instruction could be on one page, and the other part of the instruction could exist on another page. So there's 2 pages. And then for these instructions, both operands for the instruction could use memory indirect addressing. So it has a variable both for the parameters, and these variables are pointers, so it refers to a page for each one of the operands for the instruction, and then it does a dereference through them to load another address, each of which can potentially be on another page. And so an instruction can be about 6 pages for a single instruction. And this is just to say that your instructions can require a minimum number of frames, and your process, therefore, needs a minimum number of frames in order to operate. And so the maximum available number of frames is the total frames comprising all of your main memory. And there are 2 different schemes that are used, or 2 major flavors of scheme or approaches that are used to allocate the frames needed by each process to those particular processes' pages. One is called fixed allocation, and the other is priority allocation. And there are all sorts of variations, but just to give you a high-level view of the approach. And so for fixed allocation, you have an equal allocation. It's very simplistic, an equal allocation of frames to processes. And so suppose you have a total system memory comprised of 100 frames after you have allocated frames to the operating system. So the operating system is first in line. And then let's say out of these 100, you have 5 processes. So then each process gets an equal share of the number of available frames left in the system after the operating system gets its portion first. And so that would mean each of the 5 gets 20 frames. You divide that 100 up by the number of processes. Or you could also keep some of these frames free as a pool, a buffer pool, as it were, frames, so that when some process needs frames, you're not introducing page faults. Another approach is called proportional allocation, or equal priority, where the number of frames each process gets is dependent upon the size of the process. And so in this proportional allocation scheme, it depends on the size of the process greater than some minimum that is needed for all processes. And this is dynamic. It changes as the degree of multiprogramming and the process sizes change. So in this scheme, let's suppose the number of frames we have available is 64, and M is 64, and then let's define little si as the size of process pi, where that size is the number of pages. And remember that pages are the same size as frames. So we're going to define big S as the sum of all of the process sizes, pi, and that's M is the total number of frames we have in our system. And so the allocation AI of frames to a particular process pi, we take the proportion, let me set my pen here, we take the proportion of the size of the process si divided by the total size among all the processes, and we multiply that proportion by m, the number of frames that are available. And so an example that's given in the book, suppose if you had m equals 64, and let's just assume for the sake of argument that your kernel used up 2 of them. So you're going to subtract those 2 frames set aside by the kernel, and that's going to leave you with 62 frames available for all the processes. And so let's assume that the size of process P1 is 10 pages, and the size of process S2 is 127. So you take your S1 and S2 and compute S is equal to the sum of S1 and S2. That's 137. That's going to be the denominator. And for A1, the allocation of process P1, that's the 10. That's S1 divided by that total S. That's 10 over 137. We'll multiply that by M, and that's roughly equal to 4 frames for process P1. We do the same thing for process P2. So A2, allocation 2, is 127. That's S2 divided by that S over 137. Multiply that proportion by M, the number of frames. That's 57 frames approximately. Okay, so there's proportional allocation. Now, of course, when you do this proportional allocation scheme, you use process size in this previous example, but you could also use priorities instead of size. Now, of course, why is that a good thing? Well, a higher priority process is going to get the CPU more often than not selected or preferred by the short-term scheduler. And if that's the case, in order to support the quick turnaround time for those higher priority processes, allocate frames to them first so that they don't incur page faults, paying that order of magnitude slowdown in order to swap in and swap out pages to the backing store. And so if process PI generates a page fault in this approach, you select for page replacement one of its frames, and you're going to replace a frame from a process that has a lower priority number. And so in this particular case, let's assume process P1 had a higher priority than process P2, and process P1 in main memory, say, had a couple frames here. So let's say this is process P1, and then we had P2, 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 P2. So if process P1 has a higher priority and process P2 has a lower priority, if process P1 needs another frame, it's going to select a frame to evict the page from it belonging to the lower priority process. Okay, and so there are also different schemes or scopes by which you can do your replacement. You can replace pages globally, meaning that you select a victim frame from the set of all frames. So they could be from other processes. But the execution time can vary greatly, because if you evict a process's page out of an existing frame that was allocated to it, it might refer to it later, incurring another page fault. So another approach is this local replacement. Now, with this local replacement, each process is going to select only from its own set of allocated frames. So process P1 is only going to select victims from frames that belong to process P1. within the process. Now, of course, this gives you more consistent per process performance because you're not susceptible to external influences, i.e., some other process operating or stealing frames from you, impacting your performance because you have that pause for I/O because of the swap. Okay, so but this local replacement can also lead to underutilized memory, meaning that you get some minimum allocation of frames that you're not using if there's no stealing, if you will, of frames from other processes running on the system. And so another consideration when you're looking at page replacement is non-uniform memory access, or NUMA. Now, in many architectures, how they or organize them is they have a CPU that is connected. Sometimes it's on the same chip on a high-speed substrate to some memory, and these CPU memory combinations are interconnected through a bus. And so when you're going to access memory that's local to a CPU, it's very fast. So this type of access is fast. When you access memory associated with a different CPU node, say CPU 0 has an instruction that fetches something from memory 3 that's local to CPU 3, you're going to incur a slowdown or non-uniform memory access latency to go over this interconnect to set up the transaction to read that memory from another CPU's local memory. And so when you're looking at page replacement, you want to consider differential access speed to memory if you're fetching or writing memory or pages that belong to non-local memories. And so in this, when you're going to do page replacement, one of the things you want to consider is selecting a page to replace that is close to the CPU where the thread has been scheduled. And so in this case, when you modify the scheduler to schedule a thread on the same system board as much as you can, because you don't want to page in across non-local memories. And so there are operating systems that address this. One of them is Solaris, made by Sun Microsystems, which was bought by Oracle Corporation after the dot-com bust in the 2000 late 90s. And what this does, it creates something called an L group, a low latency group. It's a set of CPUs and memories that are local to one another. And whenever you invoke the scheduler and the pager, you schedule all threads of a process and allocate memory for that process within the L group so that you pay the minimum cost for this paging to and from memory because it's always local within that low latency group. And so there are considerations for multiprocessor architectures in the paging system. All right, so let's take a look at this last topic called thrashing. Now, of course, if the number of free frames is very, very scarce, a process doesn't have enough pages that are resident in memory, your page fault rate is going to be high. Now, of course, you incur a fault in order to get the page, replace an existing frame with that page swapped in from the backing store. But then what happens if things are really, really scarce, you have very few pages resident in memory for a process, you're going to have to replace it back because you're going to need some instruction or variable or data structure in that page that you just faulted out for that local allocation. And so what happens as a condition then is that you're incurring so many page faults that more time is being spent on the paging operation than executing. Because remember that execution, when you're paging in and paging out, that's an I/O operation. And so it might seem that your CPU utilization is low because you spend more time doing I/O than computation, but your process takes a really long time because this disk operation, this I/O operation, leads to a tremendous slowdown. Now that's called thrashing. And in fact, you see that on your system if you run a whole bunch of applications and all of a sudden your performance comes to a screeching halt. And so this leads to low CPU utilization. And when you get low CPU utilization, it's a pretty damning so-called death spiral that happens. you get low CPU utilization when you're thrashing, your performance is lower, and you spend less time doing I/O, or rather less time doing CPU operations, CPU bursts, and you spend more of your time doing I/O bursts. And when your operating system detects this low CPU utilization, it thinks, okay, well, I need to increase my degree of multiprogramming, so let me bring in another process into memory. Now, all of a sudden, you bring in another process into memory, and that creates more demand for the pages because that new process, it needs some minimum number of pages, and that just exacerbates the problem. And so thrashing is that condition where a process is busy swapping pages in and out. And so in order to fix thrashing, it's kind of non-intuitive. Your CPU utilization starts to plummet, but instead of increasing the degree of multiprogramming, you need to decrease the degree of multiprogramming, lessen the demand for pages by lessening the number of processes that are in memory contending for pages. Okay, so in this graph, and it's in the book, we have along the horizontal axis the degree of multiprogramming, and we have on the vertical axis our CPU utilization. And so as you increase the number of processes on your system, you're increasing the number of schedulable entities that are increasing in aggregate the total amount of CPU burst time spent, and therefore increasing your CPU utilization. So what you see is as you increase the degree of multiprogramming going to the right, you see the CPU utilization begin to climb. Now, of course, there comes a time when you start to see a decrease in CPU utilization, and that's when the demand for free frames is going to increase to the point where that demand can't be satisfied, and you get thrashing. So, of course, when you get thrashing, CPU utilization starts to drop because you're spending more and more and more time on the I/O burst, the paging in and out of swap, than you are on the CPU burst. And so that point where the CPU utilization starts to plummet or drop off precipitously as you increase the degree of multiprogramming, that's when thrashing is occurring. Okay, and so one might ask, how do you deal with thrashing? Well, let's consider why demand paging works at all. It works based on this idea of locality. And locality means that the set of instructions that you execute and the variables and or data structures you access are local to within a page. And when a process executes its instruction stream, we talk about some process, P1, and the instruction stream from instruction 0 through n-1 in the virtual address space. And so you're going to execute a bunch of operations in some location and maybe like jump to another location, execute some instructions, jump to another location, and so forth. And so the localities may overlap, but you certainly, in your execution of your instruction stream, going to switch from one locality, locality 1, to another locality. Let's call that locality 2, to another locality. Let's call that locality 3. So when you think about thrashing, why does the thrashing occur? It means that the size of the locality that you're dealing with, let's say this block of instructions within the instruction stream, is greater than total memory size. Because remember, you're going to chop up your virtual address space into chunks, and those chunks are the pages, and those pages are loaded into frames in your main memory. And so when the locality exceeds the size of the total memory that you have, and therefore availability of frames, that is going to limit the effects. You need to limit the effects by using local or priority page replacement. And so this thrashing occurs when the condition of the demand of the locality exceeds the amount of memory. And so this local or priority page replacement allows you to say, okay, well, I am going to value this particular process's usage of pages over another to satisfy this locality, because I'm going to be using addresses very frequently in a locality. And so if I satisfy that frequent access by prioritizing its demand for pages, I'm going to decrease the amount of page faults, because that means more likely than not, all of the instruction references within this locality are going to be satisfied and not cause page faults as frequently. Okay, so let's take a look at the scatter graph. And in the scatter graph, we have execution time along the horizontal axis, and we have the page numbers that are referenced on the vertical axis. And so here we have 2 points in time, point A and point B, in the execution of instructions of some thread, the instruction string. And so here we see in the scatter plot, we get this colored in portion represents access to a page, which is on the vertical axis. So here at point A, we have pages that are referenced in the execution of this process up to this execution time we're calling point A in time. And that reference is pages 18 through, looks like 24 or 25, 18 through 24. And then we also have references to pages 29 through 34. But then when we get to another point in time in the execution, point B, we see a different set of pages from the memory reference pattern for the same process. We have pages 18 through 21, and then we have pages 24 through roughly 29, and then we have pages 31 through 34. And so we see here the set of pages needed to support the execution of all of the references for the same process changes from that point in time, step A, to step B. And so the working set is based on the idea of the set of pages needed for a process to execute, and that's based on the addresses that are referenced within that instruction stream for a thread over some period of time. So let's define some time delta, and that's going to be the working set window, and that working set window is going to represent a fixed number of page references. So let's say, for example, your window was 10,000 instructions that execute. Now we have the working set size for a particular process called WSSI, and this working set size is the total number of pages referenced in the most recent period of time, delta, and that delta can vary. And so if delta is too small, it's going to encompass not the entire locality, only part of it. If delta is too large, it's going to encompass more than one locality. And if delta is infinite, that's going to be the entire set of pages or localities encompassing the entire program. And so the demand for frames is then the sum of all of the working sets for each of the processes under consideration on your system. So we sum together all the working set sizes for each of the ith process. That's going to be our demand. And so this demand is an approximation of locality. Now, of course, if the total demand for frames, i.e. the number of pages in your working set size or process, exceeds the total number of frames M, that's when you get thrashing condition. So you want to avoid that. So now what your policy then is, if your demand exceeds the total number of frames, then you're going to do one of two things. You're going to either suspend one of the processes to free up some of those frames, or you're going to swap out one of the processes. And so here's an example. We have a set of reference strings for pages, and here's a first delta, and the working set size at time t1 for a process is going to be 1, 2, 5, 6, 7. So if we look at all the different pages that are unique, that are accessed in the instruction stream, well, 1, 2, 3, 5, 6, and 7 are they. Now, then this other point in time for delta, at some other period of time, we'll call it T2, it's the same delta, our working set size is different. It's just 3 and 4. If we look at the instruction streams, it's 3, 4, 4, 4, 4, 3. It alternates a little bit here and there between 3 and 4. But the references within this window of time, that working set size is only a size 2 for pages 3 and 4. And so this is a dynamic process, and we calculate this and add up the demand for all the pages and therefore page frames needed by all your processes. and then we kick some process out if we exceed the total available frames in the system. And so how do you keep track of this? Well, one of the things you could do is set a timer that's going to wake up, fire an interrupt, and add a reference bit to your paging hardware. And for example, delta is 10,000 instructions, and after every, say, 5,000 time units, you fire an interrupt, and you keep 2 bits for each page, and each time the interrupt fires, you copy and set the values of all those bits. You copy them, and you set the values to 0. So if one of the bits in memory is still 1, that means that page is in the working set. So you're using essentially these bits as a kind of dirty bit to say not just has something been written, but has that page been referenced. And if that page has been referenced or used or read or accessed, it is in the working set after a certain amount of time. Now, this isn't completely accurate, and why is that? Well, you don't know when it happened. You know that it happened. You don't know if it happened in the first 5,000 time units or the second, but you do know it happened if that bit remains as 1. An improved way you could do this is instead of interrupting every 5,000 units and setting a bit, one of these 2 bits, every time those 5 units of time intervals transpire, you could have 10 bits. And with these 10 bits, now you can interrupt every 1,000 time units, but you're interrupting more, and that could result in a slowdown. So with these 10 bits, you know exactly when this reference happened on a finer level scale, but the trade-off is you pay the cost of having 5 times more interrupts. And so another direct approach, better than the working set size, is to look at the page fault frequency. How many times or what is the rate of page fault that happens, and use local replacement policy. And so you set some thresholds on the rate, an upper bound and a lower bound. And if the actual rate is too low, the process loses a frame. If the actual rate is too high, the process gains more frames. And so this graph is in the book. On the horizontal axis, we have the number of frames that are used, and we have the page fault rate. So if the page fault rate goes high, you get more frames, and then eventually your page fault rate goes lower. If it goes beyond the lower bound, then you decrease the number of frames. You reclaim these frames. And so you're adjusting the number of frames allocated to a process based on these thresholds for the page fault rate, and this is a lot easier to implement in the system. And so there's a direct relationship between the working set of a process and its page fault rate. The working sets, as we saw, they change over time, and you can get peaks and valleys in the page fault rate, and this page fault rate spikes in the beginning as you're faulting in those pages needed to satisfy the work set. So let's say you have some unit of time, and that work set over that delta is 5 pages long. And so in the beginning, you're going to have those 5 page faults. It's going to spike, and then as the number of pages that have been allocated to frame approaches the number of pages needed to satisfy the working set, then the number of page faults is going to start to drop, because now all those needed pages for the work set for all those localities referenced are going to be satisfied in memory, and the page fault rate precipitously declines. And so here we have some units of time. We get a spike as you start faulting in pages. Horizontal axis is time, vertical axis is page fault rate, where 1 represents a rate of 100% all of time. So we start faulting in pages until we satisfy the work set, start getting closer, and then our page fault rate drops. So then you change localities to some other block of pages, sets of blocks of pages within the virtual address space in the instruction string for the thread. And again, you start faulting in pages for that new work set. And then as you get closer to this work set size needed, those page faults go down over time. And you'll notice here, the working set, that span, it changes from one instance to the other based on the working set, because the working set changes, and it has to change as the localities changes for your thread as it executes within its virtual address space. All right. So with that, that's all I had. We will end there, and this completes our module on virtual memory. And so, as usual, please make sure you're keeping up with reading. Please make sure you are aware of these key dates. And as always, please stay healthy, stay safe, and I'll see you all on Tuesday.